Good morning, everybody. Today, at the lecture, we will discuss very complex and extremely necessary moments in your activity regarding the biopotentials of our body as a whole, and in particular, we will also discuss the conductive system of human heart, of our heart, and of course, the method for diagnosing the conducting system of the heart, electrocardiography. Very necessary method, diagnostic method, which we must understand and which we must understand physical basics of this method. So let's start our today conversation with the definition. What is the membrane potential? Since in order to talk about the potentials, we must first define what the cell membrane potential is. But first, let us discuss the history of the issue. In 1792, the Italian physiologist and physician Luigi Galvani conducted experiments with frogs. On the next day, he dried frog legs on the balcony, and it was humid outside. The wind was blowing in the street. The legs swayed in the wind and touched the metal lattice of the balcony, and the scientist noticed that at the moment of contact there was the contraction. He believed that electricity was the cause of this reduction and he thinks that the animals were the source of this electricity. I think you know that, of course, this assumption was wrong. He was opposed by the scientist Alessandro Volta, who believed that in Galvani's balcony experiment, the muscle is only a sensitive electrometer of electricity generated by the contact potential difference of different metal. A little later, Galvani's discoveries were confirmed in the works of Matteucci. He discovered the phenomenon of secondary or induced contraction, when a nerve of one neuromuscular drug was placed on the muscle of another drug and a nerve stimulus of that drug. Matteucci observed muscle contraction of both drugs. On the basis of this phenomenon, he put forward the hypothesis of a change in electrical charges of the nervous tissue when it's excited. Modern ideas about nature of bioelectric phenomena in tissues are based on the result of the work of Hodgkin, Huxley, and Katz, who in the 40s, 50s of the 20th century modified the experimentally substantiated the membrane ionic theory of Bernstein. Currently, the presence of electrical potential in living cells is due to different concentration of sodium, potassium, calcium and chlorine ions inside and outside the cells, as well as different permeability of the cell membrane for them. Let's return to definition of the membrane potential. We must say, what is this? Let's see on the slide that the membrane potential is the potential difference or difference potential, we can say, between the surface of the cell membrane and its protoplasm due to uneven distribution of the concentration of ions on the outer and inner surfaces of the membrane. And the reasons for the resting membrane potential as follows. We will say later about it, but now we must say about some let's see on the picture. On the picture you can see the cell membrane. We know that in the membrane there are two layers of what? Of lipids. I think you know this. And in this membrane there is the channels there is a channels, and through these channels, ions can go through the membrane, inside and outside. And we know that in basic stage, the normal concentration of natrium is more inside than outside, and kali opposite, not natrium. We can say sodium outside maximum in the basic statement, and potassium inside, in potassium inside, opposite, So now we should say some reasons for resting membrane potential as follows, and we must say that unequal distribution of ions on both sides of membrane. Inside the cell there is most of all potassium ions, but outside it's small. Sodium and chlor are more outside than inside. This distribution of ions is called ionic asymmetry. How I said earlier, due to this picture. And don't forget that selective permeability of the membrane for ions. At rest, the membrane is unequally permeable to various ions. I think you know this from biology information. And you must know this information about membrane, about ions, and about membrane channels, especially about membrane channels. So let's continue. Let's move on with you directly to the consideration of the physical and physiological foundations or fundamentals, fundamental information. So, membrane electrical potentials exist in virtually all cells in the body. I think you know this information. So, certain cells, such as the nerve cells and muscle cells, are capable of generating rapidly changing electrochemical impulses that are used to transmit signals along the membranes of these cells. In other cell types, such as the glandular, macrophages, and ciliated cells, local changes in membrane potentials also activate many cellular functions. We discussed with you that in a calm state there are more potassium ions inside the cell than outside. This situation is just shown in the diagram you can see. About kalium, part A. Suppose that in this case the membrane is permeable to potassium ions but impermeable to other ions. Due to the large concentration gradient, there is a strong tendency for a large number of potassium ions to diffuse out of the cell through the membrane. In the process of diffusion, they carry out positive electrical charges outside. As a result, the membrane is charged positively from the outside and negatively inside. Since the negative ions remaining inside don't diffuse out of the cells along with potassium ions. Within about only 1 millisecond, the difference potential between the inner and outer sides of the membrane, called the diffusion potential or potential of diffusion, we can say, becomes large enough to block further diffusion of potassium ions outward despite their high concentration gradient. In nerve fibers, the required potential difference is about 94 millivolts, minus 94 millivolts. Units, system international units of potential is volts, but it's very big number for our cells, so don't forget millivolts will be for our cells. So, and with a negative charge inside, you can see negative charge inside the fiber. the cell, nerve fiber, nerve cell. So the diagram also shows the sodium ion. Remember that there is a high concentration of the sodium ions outside the fiber and low concentration inside. Part B on the picture, yeah, inside natrium. More number of natrium, outside less number of natrium. So these ions also have a positive charge, but this time the membrane is highly permeable to sodium ions and impermeable to other ions. Diffusion of positively charged sodium ions into the fiber creates a membrane potential of opposite polarity compared to the membrane potential in part A, with a negative charge on the outside and positive charge on the inside. As in the first case, membrane potential within a fraction of the millisecond becomes sufficient to stop diffusion of sodium ions into the fiber. In this case, for neural fibers, the potential is about 61 millivolts with a positive charge inside the fiber, you can see. Thus, the difference in ion concentrations across a selectively permeable membrane under appropriate conditions can create a membrane potential. Yeah, you can see on the slide, left part is about kalium part and right part is about natrium, sodium part, potassium part and sodium part. Don't forget about it. Let's see it again here with about potentials and about cells. Yeah, you can see. So the level of the membrane diffusion potential that completely stops the overall diffusion of a particular ions through the membrane is called the Nernst potential for that ion. Nernst potential. The magnitude of the Nernst potential is determined by the ratio of the concentration of a specific ion on both sides of the membrane. The greater this ratio, the greater the tendency the ion to diffuse in one direction, and therefore the higher the Nernst potential. To maintain the diffusion equilibrium of ions, it's necessary that ions pass through the membrane in equal amounts in both directions. Therefore, a given difference in ion concentrations on the membrane, there is an equilibrium potential, at which the flow of ions through the membrane stops. The equilibrium potential can be determined using the Nernst equation. You can see this is the Nernst equation according to the Nernst potential. You can see how we can calculate it. The equilibrium potential, the Nernst potential, is plus or minus 61 divided by Z. What is about Z? That is ion charge, maybe positive, maybe negative. Multiply on logarithm and concentration inside the cell divide by concentration outside the cell. So when using this formula, the potential of extracellular fluid outside the membrane is usually taken to be zero, and the Nernst potential represents the potential inside the membrane. In addition, the sign of the potential is positive if the ion diffusing from the inside to the outside is negative. And negative is the ion is positive. Therefore, if the concentration of positive potassium ions inside is 10 times greater than outside, the decimal logarithm is 10 is 1. So the potential inside, according to the Nernst equation, should be minus 61 millivolts. Don't forget about this number, minus 61 millivolts. So, this was the situation where we wanted to calculate the membrane potential when the membrane is permeable to one ion. Yeah, for according this picture, maybe one ion can go through the membrane, but through the membrane can go more than one ions. And let's discuss this part. Let's look at the calculation of the diffusion potential when the membrane is permeable to several different ions. When the membrane is permeable to several different ions, the total diffusion potential depends on three factors. Following factors. Let's see. The first factor is polarity of the electric charge of each ion. So, next is membrane permeability for each ion and concentrations of the corresponding ions inside and outside the membrane. Part small I is inside and small O is outside. The formula, which is called the Goldman equation or Goldman-Hodgkin-Katz equation, allows you to calculate the membrane potential on the inside of the membrane if it's permeable to two monovalent positive ions. What? Sodium and potassium, and one monovalent negative ion, chlorine. Let's go over the formula with you. You can see. How can we calculate the potential? Yeah, how can we calculate the potential? Minus 61 decimal logarithm, concentration of natrium inside the cell, multiply on what? Membrane permeability to sodium, to sodium, plus concentration of potassium inside the cell, multiply on membrane permeability of potassium, and plus concentration of chlorine outside the cell, multiply on membrane permeability for chlorine ions, and divide by the same, but you can see natrium was firstly inside, sodium was inside, down, outside. Potassium was inside, now outside. And chlorine was outside and now inside. Be careful with this. So consider this equation. Firstly, sodium, potassium and chlorine ions are the most important ions involved in the generation of membrane potentials of nerve and muscle fibers, as well as in nerves of the nervous system. The concentration gradient of each of these ions on either side of the membrane helps determine the magnitude of the membrane potential. Secondly, the degree of contribution for each of these ions to the value of the membrane potential is proportional to the membrane permeability for this ion. So, if the membrane has zero permeability for the potassium and chlorine ions, the membrane potential is completely determined only by the concentration gradient of sodium ions, and the resulting potential is equal to the Nernst potential for sodium. This is true for any of the other two ions if the membrane is selectively permeable to only one of them. And thirdly, the concentration gradient of the positive ion directed from the inside out leads to the appearance of a negative charge inside the cell. This is due to the fact that a higher concentration of positive ions from the inner side of the membrane as compared to the outer side. Their excess diffuses outward, and in this case, positive charges go outside and anions, no negative charges, that are not capable to diffusion remain inside the cell, creating electronegativity on the inner side of the membrane. If there is a gradient for a negatively charged anion or negative charges, we can say the opposite effect occurs. For example, an excess of chlorine anions on the outside leads to a negative charge inside the cell, as negatively charged chlorine ions diffuse into the cell, leaving outside positive ions that can't diffuse. And fourth, the permeability of sodium and potassium channels undergoes rapid changes during the transmission of nerve impulses, while the permeability of the chlorine channels does not change significantly during this process. Therefore, rapid changes in sodium and potassium permeability are mainly responsible for signal transmission in nerve fibers. So now we are faced with a reasonable question. How is the membrane potential measured? How can we measure the membrane potential of the cell? The method for measuring membrane potential is theoretically simple, but its implementation in practice is often difficult due to the small size of most fibers. In the figure on the picture on the slide shows a small pipette filled with electrolyte solution. You can see. The cell membrane is pierced through with a pipette and introduced into the fiber. Another electrode, called an indifferent electrode, is placed in the extracellular fluid with an appropriate voltmeter. The potential difference between the inner and outer sides of the membrane is measured. A voltmeter is a highly sophisticated electronic device that allows you to measure very, very low voltages despite the extremely high resistance to electric current of the tip of a micropipette, the diameter of which is less than 1 micron, and the resistance is more than 1 million ohms. 1 million ohms. To register rapid changes in membrane potential during transmission of nerve impulses, the microelectrode is connected to an oscilloscope. So, let's move on to discussing the resting membrane potential of the nerve fiber. So, the resting membrane potential of a large nerve fibers, when no nerve signals are transmitted through them, is about minus 90 millivolts. Minus 90 millivolts. So, this means that the potential inside the fiber is 90 millivolt negative, then the potential of the extracellular fluid outside the fiber. Next, we will analyze all the factors that determine the level of this resting potential, but first it's necessary to describe the transport properties of the nerve fiber membrane for sodium and potassium ions at rest. Consider the active transport of sodium and potassium ions across the membrane. The name of this we can see sodium-potassium pump. You can see it on the picture. Sodium-potassium pump. So, Recall that all cells membranes of the body have a powerful sodium-potassium pump, which constantly pumps sodium ions outside the cell and pumps potassium ions into it, as shown on the figure. You can see again, sodium-potassium pump. This is an electrogenic pump, since more positive charges are pumped outward than inward. 3 sodium ions for every 2 potassium ions, respectively. As a result, a general deficiency of positive ions is created inside the cell, leading to a negative potential on the inside of the cell membrane. Sodium-potassium pump also creates a large concentration gradient for sodium and potassium across the nerve fiber membrane at rest. Leakage of potassium and sodium through the nerve fiber membrane. On the right figure shows a channel protein in the nerve fiber membrane called sodium-potassium channels through which potassium and sodium ions can pass. Potassium leakage is especially significant since the channels are more permeable to potassium ions than sodium, normally about 100 times. This difference in permeability is extremely important in determining the level of the normal resting membrane potential. Normal resting membrane potential. So, now, consider with you the origin of the normal resting potential. Who contributes to the origin of the resting membrane potential? Contribution of the potassium diffusion potential. Suppose that the only movement of ions across the membrane is the diffusion of potassium ions through open channels between the potassium symbols K+, we can see, inside and outside the membrane. Due to the high ratio of concentrations of potassium ions inside and outside, 35 part divided by 1 part, 35 and 1, inside 35, outside 1, the corresponding Nernst potential is minus 94 millivolts, the result of multiplying on logarithm of 35 equal to 1.54 by minus 61 millivolt. According to Nernst potential, we said earlier about it. Therefore, if potassium ions were the only factor creating the resting potential, the potential inside the fiber would be minus 94 millivolts as shown in the figure you can see. Minus 94 millivolts. This is a contribution of the equilibrium potential potassium, we can say. So, sodium diffusion across the nerve membrane also contributes, not only potassium. So, on the figure, the situation has already been supplemented by a small permeability of the nerve fiber membrane for the sodium ions associated with an insignificant diffusion of sodium ions through the sodium-potassium leaks channels. The ratio of sodium ions concentration inside and outside the membrane is 0.1. Therefore, the calculated Nernst potential inside the membrane is plus 61 millivolts. But in the figure also shown is the Nernst potential for diffusion of potassium ions. Equal to minus 94 millivolts. Minus 94 millivolts, you can see this part. How do they interact with each other and what will be the total potential? To answer, you need to use the Goldman equation given earlier. Intuitively, it can be assumed that if the membrane is highly permeable to potassium ions and only slightly permeable to sodium ions, then the diffusion of potassium ions make a much greater contribution to the creation of the membrane potential than the diffusion of sodium ions. Normally, the permeability of the nerve fiber membrane for potassium ions is about 100 times higher than for sodium ions. Using this value in the Goldman equation gives a potential within the membrane of about minus 86 millivolt, which is very close to potassium potential shown in the figure. So, the contribution of the sodium-potassium pump. As shown in the figure, you can see, the sodium-potassium pump provides an additional contribution to the value of the resting potential due to the constant pumping of three sodium ions outward in exchange for the pumping of 2 potassium ions inside, which causes a constant loss of positive charges from the inner side of the membrane. This increases the degree of electronegativity within the membrane by about minus 4 millivolt in addition to that generated by simple diffusion. Consequently, the total membrane potential, full membrane potential, we can say, with the combined action of all factors is minus 90 millivolts. This rest potential, we can say, of the cell. Rest potential of the cell. So, let's continue. Having discussed the resting potential of the nerve fiber and having learned its meaning, we can already proceed to discussing the action potential of nerve fiber. In nerve fibers, signals are transmitted using action potentials, which are rapid changes in membrane potential that propagate rapidly along the membrane of the nerve fiber. Each action potential begins with a rapid shift in the resting potential from a normal negative value to a positive value. Then it returns almost as quickly to a negative potential. And when a nerve signal is transmitted, the action potential moves along the nerve fiber up to its end. The figure shows the changes that occur on the membrane during the action potential, with the transfer of positive charges to the inside of the fiber at the beginning and the return of the positive charges to the outside at the end. So, the action potential is divided into phases. The first of these is resting stage, resting phase. First phase is resting phase. And this stage and this phase is represented by the resting membrane potential, which precedes the action potential. The membrane is polarized during this stage due to the presence of a negative membrane potential of minus 90 millivolt. You can see on the picture. This is followed by the phase of depolarization. The next phase after resting is depolarization. At this time, the membrane suddenly becomes highly permeable to sodium ions, allowing a huge number of positively charged sodium ions to diffuse into the axon, into the cell. The normal polarized state of minus 90 millivolt is immediately neutralized by the positively charged sodium ions, which enter the interior. As a result, the potential rises rapidly in the positive direction. You can see rapidly, 0.1 millisecond for this. This process is called depolarization. In large nerve fibers, a significant excess of positive sodium ions entering the interior usually leads to the fact that the membrane potential slips beyond the zero level, becoming slightly positive. In some of the smaller fibers, as in most neurons of the central nervous system, the potential reaches the zero level without jumping in. And then comes the phase of depolarization after overshoot. Within a few fractions of a millisecond after a sharp increase in the permeability of the membrane for sodium ions, sodium channels begin to close, and after that, potassium channels begin to open. As a result, the rapid diffusion of potassium ions outward restores the normal negative resting membrane potential. This process is called membrane repolarization. Now, firstly, resting phase, depolarization, overshoot, and repolarization. This is action potential of the nerve cells. For a more completely understanding of the factors that cause depolarization and repolarization, it's necessary to study the features of two other types of transport channels in the membrane of the nerve fiber: voltage gate or electrically controlled sodium and potassium channels. Let's start with sodium channels. We can see on the picture sodium channels. So, an electrically controlled sodium channels is a necessary participant in the process of depolarization and repolarization during the development of the action potential in the membrane of the nerve fiber. The figure shows a voltage gate sodium channels in three different states. This channel has two gates. One is near the outer part of the channel, which are called activation gates, and the other is near the inner part of the channel, which are called inactivation gates. You can see activation gates and inactivation gates. So, the left side of the figure on picture shows the state of these gates at rest, when the resting membrane potential is minus 90 millivolts. Under these conditions, the activation gate is closed and prevents the entry of sodium ions into fiber. You can see activation gates are closed. Sodium channels activation. Sodium channels activation after rest. You can see firstly rest phase, after that activation of sodium channels. When the resting membrane potential shifts toward less negative value, rising from minus 90 millivolts towards 0 millivolts, at a certain level, usually between minus 70 minus 50 millivolts, a sudden conformational change of the activation gate occurs. As a result, they go into a completely open state. This state is called the activated state of the channel, in which sodium ions can freely enter through it into the fiber. The sodium permeability of the membrane increases in the range from 500 to 5,000 times. Inactivation of After activation will be inactivation of sodium channels. The right side of the figure shows the third state of the sodium channels. The increase in potential that opens the activation gate closes the inactivation gate, parallel processes. However, the inactivation gate closes within a few tenths of a millisecond after the activation gate is opened. This means that the conformational change leading to the closing of the inactivation gate is a slower process than the conformational change that opens the activation gate. As a result, a few tenths of millisecond after the opening of the sodium channel, the inactivation gate closes and sodium ions can no longer penetrate into the fiber. From this moment on, the membrane potential begins to return to the resting level. The repolarization process begins again, and etc., etc., etc. But we must not forget about another important characteristics of the sodium channel inactivation process. The not to be young, maybe you know this name. The inactivation gates don't reopen until the membrane potential returns to a value equal to or close to the level of the initial resting potential, membrane potential. In this regard, reopening of the sodium channels is usually impossible without preliminary repolarization of the nerve fiber. So, it was the sodium part, sodium channels. Potential gate, potassium channels. Let's see about it, let's discuss it. The figure on the slide shows us the voltage gate potassium channel in two states. On the left, at rest, and at the end of the action potential. Right part. At rest, firstly, rest phase. The gate of the potassium channels is closed, you can see, and this prevents the release of the potassium ions into the external environment. When the membrane potential shifts from the minus 90 millivolt towards 0 millivolt, this change in potential causes a conformational opening of the gate, which allows enhanced diffusion of potassium ions outward through the channel. However, since the opening of the potassium channels occurs with some delay, most of them open at the time when sodium channels begin to close due to their inactivation. Thus, a decrease in sodium entry into the cell and simultaneous increase in potassium exit from the cell together accelerate the repolarization process, leading to a complete restoration of the resting membrane potential within a few fractions of a millisecond. Don't forget about it. Now, let us discuss with you the events that underlie the action potential, namely their sequence. AP is action potential. So, the figure, this big figure, shows us the successive events occurring during and shortly after the action potential. The lower part of the figure shows changes in membrane conductivity for sodium and potassium ions. What happens at rest before the action potential begins? At rest, before the onset of the action potential, the membrane conductivity for potassium ions is 50 to 100 times higher than for sodium ions. But why? This is due to the significantly higher permeability of the leakage channels for potassium ions as compared as sodium ions. However, when an action potential arises, sodium channels are instantly activated and the membrane conductivity for sodium ions increases up to 5,000 times. Then, within a fraction of millisecond, the inactivation process closes the sodium channels. The onset of action potential development also affects electrically controlled potassium channels, with their slower opening beginning a fraction of a millisecond after the sodium channels open. Really parallel process. At the end of the action potential, the return of the membrane potential to a negative level causes the potassium channels to return to their original closed state, but only after a delay of a millisecond or more. The middle part of the figure shows the ratio of conductivity for sodium and potassium ions at each moment of the action potential. The action potential itself is presented above. During its initial part, the sodium-potassium conductivity ratio increases more than 1000 times. Consequently, much more sodium ions enter the fiber than potassium ions come out. That is why, at the beginning of the generation of action potential, the membrane potential becomes positive. After that, sodium channels begin to close and the potassium channels open. After, the conductivity ratio shifts in favor of high potassium conductivity and low sodium conductivity. This allows potassium ions to escape very quickly to the outside with virtually zero sodium ion current to the inside. As a result, the action potential quickly returns to its original level. But you and I understand that not only potassium and sodium provide the development of the action potential. At the beginning, we said that there are also anions and calcium ions in the cell. Consider their role of development of action potential. Negatively charged ions, we can say anions, that don't penetrate the membrane. Inside the nervous fiber there are many negatively charged ions that can't pass through the membrane channels. Anions of protein molecules and many organic phosphate, as well as sulfate compounds and etc. Since these ions can't leave the action, any lack of positive ions inside the cell leads to an excess of non-penetrating through the membrane of negative ions. Therefore, anions are responsible for negative charge within the fiber in the presence of a general deficiency of positively charged potassium ions and other positive ions. Secondly, what is about calcium ions? The membranes of almost all cells in the body have a calcium pump, similar to a sodium pump, and in some cells, calcium ions together with sodium ions or instead of them participate in the development of the action potential. A calcium pump, like as a sodium pump, pumps calcium ions from inside the cell membrane to outside, or inside the endoplasmic reticulum of the cell, creating a calcium ion concentration gradient of about 10,000 times. At the same time, The concentration of calcium inside the cell is 4 orders of magnitude lower compared to the external concentration. In addition, there are electrically controlled calcium channels. These channels are somewhat permeable to both sodium and calcium ions. When they are open, both ions enter the interior of the fiber, which is why these channels are also called calcium-sodium channels. Calcium channels are activated slowly. Their activation takes about 10-20 times longer than sodium channels. Because of this, they are called slow channels, as opposed to sodium channels called fast channels. The concentration of calcium ions in the extracellular fluid also has a significant effect on the potential level at which sodium channels are activated. Under conditions of a lack of calcium ions, the sodium channels are activated with a very slight increase in the membrane potential from the norm, strongly negative level. Consequently, the nerve fiber becomes highly excitable, it at times spontaneously discharging by repeated impulses without irritation. In fact, only when the concentration of calcium ions drops by 50% below normal, spontaneous discharges appear in some peripheral nerves, often leading to muscle tetany. This is sometimes fatal due to titanic concentration of the respiratory muscles. So far, we have discussed changes in the sodium and potassium permeability of the membrane during the development of an action potential without explaining what stimulates its emergence. Let's move on to the explanation. First, at rest, action potential don't arise in the membrane of a normal nervous fiber. However, any action that causes a sufficient displacement of the membrane potential from minus 90 mV to 0 mV leads to the opening of many electrically controlled sodium channels. This provides a quick entry of sodium ions into the fiber and leads to a further rise in the membrane potential. As a result, the number of open electrically controlled sodium channels increases, which is accompanied by a further increase in the flow of sodium ions inside. This process is a so-called positive feedback vicious circle, which, if the feedback is strong enough, continues until all voltage gate sodium channels are activated. Then, over the next fraction of a millisecond, an increase in membrane potential causes the sodium and potassium channels to close, and the action potentials so soon ends. But the action potential don't arise until the initial shift of the membrane potential becomes sufficient to create a vicious circle. This will happen when the number of sodium ions entering in the fiber becomes more than the number of potassium ions leaving the fiber. This usually required a 15 or 30 millivolts rise in the membrane potential. Consequently, in large nerve fibers, a sudden rise in the membrane potential from minus 90 millivolt to about minus 65 millivolt usually leads to an explosive development of the action potential. And in this case, the level minus 65 millivolt is called the stimulation threshold. Earlier, we discussed the process of the emergence of an action potential is one section of the membrane. However, an action potential that occurs anywhere in excitable membrane usually excites adjacent portions of the membrane, leading to the propagation of the action potential across the membrane. This mechanism is shown in the picture on the slide. Let's consider in the order. Part A, upper part, shows a nerve fiber at rest. And part B shows a nerve fiber excited in its middle part. So, in the middle of the fiber, the permeability to sodium is sharply increased. The arrows show the local circular currents flowing from the depolarized regions of the membrane to the adjacent unexcited regions. These currents arise in connection with the transfer of positive electric charges through the depolarized membrane in the form of sodium ions diffusing into the fiber, which then propagate over several millimeters in both directions along the axon axis or nervous fiber axis. In large myelinated nerve fibers, these positive charges at a distance of 1-3 mm increase the membrane potential to values above the threshold. As a result, sodium channels immediately open in these new areas, as shown in the figure in parts C and D, which is the basis for the propagation of the action potential. These new light depolarized areas intensify local circular currents flowing further along the membrane, gradually depolarizing more and more distant parts of it. Thus, the depolarization process spreads along the entire length of the fiber. This depolarization along a nerve or muscle fiber is called a nerve or muscle impulse, respectively. So, direction of distribution. The action potential spreads along the excitable membrane in all directions from the side of the stimulus, including along all branches of the nerve fiber, until the entire membrane is depolarized. Also, for excitable cells, the principle all or nothing is characteristic, which consists in the following. Excitable tissue in response to the action of stimuli does not respond to irritation if its value is insufficient below the threshold, or responds with a maximum response if irritation reaches the threshold. With a further increase in the strength of irritation, the magnitude and duration of tissue response don't change. Therefore, in order to continue the propagation of excitation along the fiber, it's necessary that the action potential value be higher than the threshold value. So, but how is the restoration of the concentration gradient of sodium and potassium ions after action potentials? Carrying out each action potential along the nerve fiber slightly reduces the difference in sodium and potassium ions concentrations inside and outside the membrane, since sodium ions diffuse inward during depolarization and potassium ions outward during repolarization. For a single action potential, these changes are so small that can't be measured. Indeed, from 100,000 to 50 million impulses can pass through a large nerve fiber before the concentration difference reaches the level at which the conduction of the action potential stops. Despite this, over time it becomes necessary to restore of the concentration difference for sodium and potassium ions on both sides of the membrane. This is ensured by the operation of the sodium-potassium pump. This means that sodium ions that entered the cell during the action potential and potassium ions that come out should be returned by the sodium-potassium pump to their original position. Since this pump requires energy to operate, recharging the nerve fiber is an active metabolic process that uses energy supplied by the energy system of the cell that synthesizes adenosine triphosphate. The figure shows that with an increase in frequency of impulses, the nerve fiber produces excess heat, which is a measure of the energy consumption for recharging. So, in some action potentials, there is a so-called phase plateau. Sometimes the excited membrane does not repolarize immediately after depolarization. Instead, the potential remains near the peak of the action potential at the plateau level for many milliseconds before repolarization begins. The graph clearly shows that the plateau significantly increases the repolarization period. Plateau phase. This type of action potential is characteristic of cardiac muscle fibers, where the plateau duration reaches 0.2 to 0.3 seconds, and the resulting contraction of the heart muscle lasts just as long. The plateau is caused by a combination of several factors. First, in the heart muscle, two types of channels are involved in the process of depolarization. Ordinary gated sodium channels called fast channels and voltage gate calcium sodium channels which open slowly and therefore they are called slow channels. The opening of fast channels provides the ascending part of the action potential at the slow calcium sodium channels that remain open for a long time, through which mainly calcium ions enter the fiber and responsible for the action potential plateau. Calcium ions can create the plateau phase. A second possible factor partially responsible for the plateau is that voltage-gated potassium channels open more slowly than unusual, often with little or no opening until the end of the plateau. This delays the return of the membrane potential to its normal negative value of minus 18 minus 19 millivolts. The process of the emergence and of the action potential in a cell. What happens if we give a weak electrical stimulus on the cell? A weak negative electrical stimulus may not excite the fiber. However, when the stimulus is intensified, a moment comes when arousal arises. In the figure, we see the effect of consistently applied stimuli of increasing strength. A very weak stimulus at point A changes the membrane potential from minus 90 to minus 85 millivolt. But this change is not enough for development of automatic regenerative process necessary for emergence of an action potential. First part. Secondly, at point B, the strength of the stimulus is greater, but its intensity is still insufficient. This is threshold, less than threshold. However, Each of these weak stimuli induced a local change in membrane potential lasting 1 millisecond or more. These local potential changes are called local potentials. But if they are not able to cause an action potential, they are called subthreshold potential. Subthreshold potential. At point C, the stimulus is even stronger. This time, the local potential has reached the minimum level necessary for emergence of the action potential, called the threshold level, but the action potential appears only after a short latency period. At point D, the stimulus is even stronger, the amplitude of the local potential is greater, and the action potential arises after a shorter latency period. Consequently, even a very weak stimulus causes local changes in the membrane potential, but the intensity of local potential must rise to a threshold level before an action potential arises. It's impossible to evoke a new action potential in an excitable tissue as long as the membrane of the excited fibers remain depolarized due to the development of the previous action potential. This is due to the fact that soon after the action potential arises, sodium channels or calcium channels or both type of channels are inactivated, and an excitatory signal of any strange acting on the tissue at this moment can't open the inactivation gate. The only condition for their reopening is return to the membrane potential to the initial or close to the initial level. Then, within a small fraction of a second, the inactivation gates of the channels open and it becomes possible to develop a new action potential. The period during which it's impossible to evoke the second action potential, even with a strong stimulus, is called absolute refractory period. Absolute refractory period, you can see. So, after that, now let's move on to discussing the heart of human body, namely everything that is connected with an electrical part of the heart, conducting system of our heart. You and I will consider the electrical phenomena that occur in human heart. What is the conductive system? It's a system that generates impulses that cause a rhythmic contraction of the heart muscle and a system that conducts these impulses through the heart. The figure shows us the diagram of the cardiac conduction system. We have a sinus node, pacemaker. After that, impulses go through the intermodal pathways. After that, impulse come to AV node, atrioventricular node. After that, AV bundle, atrioventricular bundle. This is GIS bundle. After that, right and left legs of the bundle GIS. And after that, it divides by Purkinje fibers. The terminal branching of the legs of the GISA bundle, along with which the impulses reach the contractile of myocardium. For the heart as a whole, automaticity is a characteristic property. Automation is ability of some heart fibers to self-excite and cause rhythmic contraction of the heart. The cells of conductive system on heart have the ability to automation. So, You listened to the basic concepts of electric charge, tangent, potential difference, electric field, and so on the last lecture. Now you and before lectures. Now our task is to put these basic physical phenomena on the human body. We have made out with you that potentials, that is, charges, run along our conducting system in the heart. But we also know that the function of cardiac conduction system can be impaired in various diseases. Or can we register these changes with you? Definitely, yeah. The method of recording the electrical activity of the conducting system of our heart is well-known electrocardiography. Using this method, we register the conduction of action potential in atypical cardiomyocytes. During the propagation of excitation in the myocardium, the heart becomes a source of electric current, which is conducted into the surrounding tissues. Weak currents are also conducted to the surface of the body. If the electrodes are placed on the skin at points located on both sides of the heart, it's possible to register the potential difference associated with conduction of the cardiac impulse. So, electrocardiogram. This electrocardiograph we have in our department and use it in our practice lesson and laboratory work. Before discussing the elements of the cardiogram in detail, let's first discuss some physical points. We know with you that impulse is important in the development of the action potential, namely the threshold value of the impulse and the work of ion channels. We know with you that the phenomena of depolarization and repolarization occur in excitable cell, which are directly related to a change in charge. And these processes are repeated in the heart all our life. But you and I must decide on the physical model of the heart. In physics, when there are two connected charges, then this is certainly connected with a dipole system when there are two opposite charges equal in magnitude and connected into a single system. Let's take a closer look at this. In physics, there is a such thing as an electric dipole. It is an electrically neutral system consisting of point and equal in absolute value positive and negative electric charges. The dipole moment of an electric dipole is a vector modulus of which is P equal Q multiplied on L. The direction of the electric dipole vector from the negative pole minus Q to positive plus Q. As a whole, this system of charges is electrically neutral. An electric dipole is a model that corresponds well to the structure of molecules, some type of their interaction which is with each other, their behavior in constant and alternating external electric field. In a non-conductive medium, an electric dipole can persist for an arbitrarily long time. But in a conducting medium, under the action of the electric field of the dipole, displacement of free charges occurs. The dipole is screened and ceased to exist. To maintain the dipole in a conductive medium, an electromotive force is required. Let two electrodes are introduced into a conducting medium, for example, into a vessel with an electrolyte solution, connected to a constant voltage source. Then, constant charges of opposite things will be maintained on the electrodes and an electric current will arise in the medium between electrodes. The positive electrode is called the current source and the negative electrode is called the current drain. As a result, this two-pole system in a conducting medium consisting of a source and a current drain or runoff is called an electric dipole generator or current dipole. The distance between source and runoff of the current L is called the current dipole arm. The electrical activity of the heart can be simulated using a dipole equivalent electric generator. The dipole view of the heart underline Einthoven lead theory, according to which the heart is a current dipole with a dipole moment, which rotates, changing its position and points of application during cardiac cycle. Einthoven stood at the origin of the method of electrocardiography in the form in which we now use. According to Einthoven's theory, the heart is located in the center of an equilateral triangle, the verticals of which are right hand, left leg. The vertices of the triangle are equidistant both from each other and form the center of triangle. Therefore, the potential difference taken between these points are projection of heart dipole moment on the sides on the triangle. Pairs of points between which biopotential differences are measured have been called leads in physiology since the time of Einthoven. Thus, Einthoven's theory established a connection between a difference in the biopotential in the heart and the potential difference recorded in the corresponding leads. And this is a vector analysis. So, a normal ECG is a set of waves and intervals as reflect electrical processes in the heart. The P leads reflect the process of atrial depolarization. QRS complex reflects the processes of atrial repolarization and depolarization of the ventricles. And T's reflects the process of ventricle repolarization. And also remember, electrocardiography reflects the process of conducting waves of depolarization and repolarization along the conducting system of the heart and does not reflect the contraction of the heart. The contraction of the heart is a mechanical process. It's preceded by electrical process with which we record on ECG, on electrocardiogram. So, each of the measured potential differences in electrocardiography is called a lead. Usually, when conducting an ECG, we record 12 leads, as usually. 3 standard bipolar limb leads. The term bipolar lead means that an electrocardiogram is recorded using 2 electrodes located on either side of the heart, for example, on the extremities. Therefore, a lead can't be a single electrode and a wire connecting it to the electrocardiograph. The lead is a combination of 2 electrodes, the wires from which go to the device. In this case, a complete closed loop is formed, including the patient's body and the electrocardiograph. Standard lead 1. To register the standard lead 1, the negative input of the electrocardiograph is connected to the right hand and the positive input to the connected to the left hand, positive. Thus, when the point of attachment of the right arm to the chest becomes electronegative compared to the point of attachment of the left arm, the electrocardiograph registers a deviation in the positive direction, so above the zero isoelectric line. Like this, isoelectric line, zero line. And conversely, when the point of attachment of the right arm to the chest become electropositive compared to the point of attachment of the left arm, the electrocardiograph registers as a deviation in the negative direction, so below the zero line. Upper and below the zero line may be positive upper, negative below. Standard lead 2. To register standard lead 2, the negative input of the electrocardiograph is connected to the right arm and the positive input connected to the left leg. Therefore, when the right arm is electronegative compared to the left leg, the electrocardiograph records a positive deviation from a zero line. Upper than zero line. Standard lead 3. To register a standard lead 3, the negative input of the electrocardiograph is connected to the left arm, and the positive input is connected to the left leg. Therefore, the electrocardiograph registers a positive deviation if the left arm is electronegative compared to the left leg. The drawing depicts a triangle around the location of the heart, which is called Einthoven's triangle. You can see Einthoven's triangle. This diagram shows that both arms and left leg form the apex of the triangle surrounding the heart. The two vertices in the upper part of triangle represent the points from where electric current travel through the conductive media of the body to upper limbs. The lower peak is the point from where the current spreads to the left leg. Einthoven's law. Einthoven's law says us, if at a given moment the value of electrical potentials in two standard leads out of 3 is known, then the magnitude of the potentials of the third lead can be determined mathematically by simply adding the first 2. When adding, you must take into account the plus and minus signs. For example, suppose that at the moment the potential of the right hand is minus 0.2 millivolts, so negative. The potential of left hand is positive, plus 0.3 millivolt, and the potential of left feet plus 1 millivolt, as shown. Taking into account the reading of the measuring devices, it can be seen that a positive potential of 0.5 millivolt plus 0.5 millivolt is currently recorded in lead 1. You can see. Because this is the difference between minus 0.2 in the right hand and plus 0.3 in the left hand. In lead 3, a positive potential 0.7 is recorded, and in lead 2, a positive potential 1.2 millivolt, because this is the moment potential difference between the corresponding pairs of limbs. Note that the sum of potentials of lead 1 and 3 is equal to the magnitude of the potential recorded in lead 2. Because 0.5 plus 0.7 is 1.2. This mathematical principle, called Einthoven's law, is valid at any given moment when 3 standard bipolar electrocardiogram leads are recorded. So, often An electrocardiogram is recorded using an electrode placed on the anterior surface of the chest, directly above the heart at one of the 6 specific points. This electrode is connected to the positive input on the electrocardiograph. The second negative electrode, which is called indifferent, is connected through additional electrical resistance to the right hand, left hand, and left leg at the same time. Usually, 6 chest leads are recorded one after the other. In this case, the chest electrode is sequentially moved to each of the 6 points indicated in the diagram. These leads are known as V1, V2, V3, V4, V5, and V6. Another widespread lead system is amplified unipolar limb leads. In these leads, 2 limbs are connected through additional electrical resistance to the negative input of the electrocardiograph, and the electrode located on the third limb is connected to the positive input. If the positive electrode is one on the right arm, lead AVR is recorded. AVR, enhanced right arm abduction. If the electrode of the left arm, lead AVL on the left arm is recorded if the electrode on the left leg. Lead IV is recorded. AVF from the left leg. So, to understand how cardiac abnormalities are reflected in the electrocardiographic curve, we must become familiar with the concepts of Victor and Victor analysis in relation to the electrical potentials of the heart and surrounding tissues. Earlier we discussed with you that electric current propagates in the heart in a certain direction at every moment of the cardiac cycle. The vector is an arrow that characterizes the magnitude and direction of the electrical potential difference. The arrow on the left part, we can see on the left part picture. The arrow is always directed from minus to plus, so in the positive direction. In addition, it's customary to depict the length of the arrow in proportion to the magnitude of the potential difference. The figure is highlighted in red and marked with minus sign depolarization between the ventricular septum and the ventricular myocardium located under the endocardium in the apex of the heart. At this moment, electric current flowing from the excited internal structures of the ventricles to the unexcited external ones are indicated on the diagram by long red arrows. The red arrows show the currents flowing inside the heart chambers directly from the electronegative to the electropositive part of the myocardium. In general, currents going down from the base of ventricles to the apex of the heart and more powerful than currents going in opposite direction. Therefore, the total vector reflecting the potential difference at a given moment is directed from the base to the apex, of our heart. It's called by mean moment vector. Second diagram. In the diagram, the average torque vector is indicated by a long this long arrow, black arrow, So, passing through the center of the ventricles from the base to the apex, again, this big, long, black arrow. Since the total currents are large and the potential difference is large, the vector of great length is shown. The direction of a vector is indicated in angular degrees. Upper part. If the vector is slightly horizontal and point to the left its direction is 0 degrees, as shown in the figure, to the right. From this 0 point clockwise, the reference scale begin. So, if the vector is perpendicular to the bottom, for example, this vector perpendicular to the bottom, its direction corresponds to plus 90 degrees. If the vector is horizontal at the points to the right, its direction is plus 180. If the vector is perpendicular upward, its direction is minus 90 degrees or plus 270 degrees. The average direction of the vector during the propagation of the depolarization wave along the ventricle myocardium is called the average QRS vector. Normally, its direction is approximately plus 59 degrees, as shown in the figure. You can see this part. The passing through the center of the circle at the angle of plus 59 degrees. This means that most of the time the depolarization propagates the apex of the heart, remains electropositive with respect to the base of ventricles. And all our leads is the result of this vector analysis. All our leads, all our T's in the electrocardiograms, this is the vector analysis. Only vector analysis between and in the Einthoven triangle. So now I can say you thank you for your attention, and I must say you goodbye, and so on.